let's do some example numerical problems. The first one that I will do is from chapter 12 on the sun, chapter 12, and it is on page 325, and it is problem number 1. And first thing to do is to carefully read the problem, of course. Using the values in the appendix, how many times larger in diameter is the sun than the earth? So the answer to this problem is going to be the ratio of the diameter of the sun to the diameter of the earth. Now in astronomy, for any data that applies to the sun, we label it by a circle with a dot in it, and any data that applies to the earth, we label it by a circle with a cross in it. So the diameter is twice the radius of the sun, divided by twice the radius of the earth. So you see the 2's cancel out. So the answer to the problem is going to be the radius of the sun divided by the radius of the earth. Now we have to introduce ourselves to the table of astronomical data that is in the back of the book, and there are about many pages here, all of data about the galaxies, the planets, and the universe in whole. And we will be using this continuously throughout the course, so you must find out where it is and start to make use of it. So at that data table, what we find out is that the radius of the earth is, the radius of the sun rather, the radius of the sun is 6.96 times 10 to the 8th meters. Now the radius of the earth is given in kilometers. It's 6,378 kilometers, and that's equal to 6,378 times 10 to the 3 meters. And if we move the decimal point back 2 places, it's equal to 6.378 times 10 to the 5th meters. So if we put this underneath to perform the division, the first thing that we do is divide the number by the number. So we reach for our calculator and we punch in 6.98 and we divide it by 6.378 and we get 1.09. And now we get the correct powers of 10, and you notice that this would be a 10 to the 6, move it back 3 decimal places, and we get a 6, not a 5. So correct that to a 6. Now we know that when we divide powers of 10, we have a rule that a to the n over a to the m is equal to a to the n minus m. Therefore, that means that 10 to the 8th divided by 10 to the 6th is equal to 10 squared. So this is times 10 squared. So if we move the decimal place 2 places, decimal point 2 places, we find that the answer to the problem is 109. And the radius of the earth is, the radius of the sun is 109 times larger than the radius of the earth. Then the next problem I'm going to do is back in chapter 4. And it is number 1. So the next problem is chapter 4. And it is on page 114. And it is number 1. Now this was a problem that was on your quiz too. So we read the problem. Use the sun's distance of 106 million kilometers to calculate how long light takes to travel from the sun to the earth. Any traveling object has a relation that the speed is equal to the distance divided by the time. So I'll put it down here so I have room to work. Speed equals distance divided by time. Now, if I multiply both sides of this equation by the same object, then the equation continues to be true. So I'm going to multiply this side by time divided by speed, and I'm going to multiply this side by time divided by speed also. And what you observe is that on this side, the speeds cancel out, and you're left with time. And on this side, the times cancel out, and you're left with distance over speed. So we have inverted the standard equation to find out time is, since that's what we're looking for. Now, in this problem, we're giving that the distance is equal to 150 million kilometers. Means 150 times 10 to the 6th kilometers. So let's convert that to meters, because we work all of our problems in meters. So it's equal to 150 times 10 to the 6th times 10 cubed meters. Now, we know from our properties of exponents that any base to the power m times the same base to the power n is n plus m. That means 10 to the 6th times 10 to the cube is equal to 10 to the 9th. So this is equal to 150 times 10 to the 9th power meters. Okay, now I'm going to change that to, well, I'm going to leave it like it is for the moment. Now the speed that we're dealing with is the speed of light, which we can look up in the table in the back of the book, or by this time you have it from memory. Speed equals c equals 3.0 times 10 to the 8th meters a second. Now our time, the answer to the problem, answer equals time equals distance over speed. So it is equal to 150 times 10 to the 9th divided by 3.0 times 10 to the 8th. Now, first we divide the numbers. 3 into 150 is 50. And now we have powers of 10 again to divide. 10 over to the 9th over 10 to the 8th is 10 to the 1st. So it's times 10 to the 1st. So the answer is 500 seconds. Now if you divide this by 60, then you get 8 minutes and something like 20 seconds left over. So the amount of time that it takes the sun to reach the Earth is either 500 seconds or 8 minutes, 20 seconds, as you prefer. And this was a problem that was on your quiz 2. The next problem was also on your quiz 2. It's the same page, and it's number 3. A frequency commonly used for cell phones, wireless internet, and even in microwave ovens is 2.4 gigahertz. Now, giga is a parameter that stands for 10 to the 9th. What is the wavelength of this radiation? So what we're given in this problem number 3 is that the frequency, which we use the symbol mu for, equals 2.4 gigahertz, which is equal to 2.4 times 10 to the 9th hertz in the units that we use. Now we know that the speed of a traveling wave is equal to the wavelength times the frequency. So if we divide both sides by the wavelengths, then we get the answer to the problem, the frequency, is equal to the speed divided by I'm going the wrong way. I have to remove this, and now what we're looking for is the wavelength. So we know that for any traveling wave, the speed is given by the wavelength times the frequency. So if we divide both sides by the frequency, then we get that the wavelength, which is what we're looking for, is the speed divided by the frequency. So let's do that. And again, we're dealing with the speed of light. So c is equal to 3.0 times 10 to the 8th meters a second. So 3.0 times 10 to the 8th. And our frequency was given as 2.4 times 10 to the 9th. So if we perform the division, we get 1.2 times 10. Now what powers of 10? We have 10 to the 8 over 10 to the 9, And the general rule is that a to the n divided by a to the m is a to the n minus m. So this is equal to 10 to the 8 minus 9 equals 10 to the minus 1. 1.2 times 10 to the minus 1. And what we have here is a wavelength, so this is in meters, and we move the decimal point back one place, and we get 0.12 meters for our answer to the problem. Now the next problem we're going to deal with is number 10 on the same page. So at any time, of course, you can freeze these frames and look at the solution for as long as you want to, and scroll back and see the top as well. So now we'll go forward to number 10 on the same page. You are analyzing a radio spectrum of an outer part of a distant spiral galaxy. A spectral line expected to be at 21 centimeters is instead measured to be at 21.010 centimeters. Is the outer part of the galaxy rotating toward or away from you? And by how much? How fast is that galaxy part rotating? Now, in this case, the wavelength has been stretched out. The wavelength has been lengthened. That we say that this wavelength has moved towards the red, because red has longer wavelengths in our eyes than blue. So it moves towards longer wavelengths. We say it's red shifted. If the wavelength is stretched out or red shifted, it's a signature that the object is moving away from us. So the answer to part A is away. Now they want to know by how much. So we have to know that we have to use the Doppler equation, that v, the velocity of the object, divided by the speed of the wave, in this case c, the speed of light, is equal to the amount of shift divided by the original wavelength. And the amount of shift is the observed wavelength minus the actual wavelength that was emitted, the wavelength that you see in the lab. So in this problem, delta lambda is equal to 21.010 minus 21.000 equals 0.10. So we can form the equation for the velocity. The velocity over c is equal to delta lambda over lambda. Now we can multiply both sides of the equation by c, and they cancel out on this side, and what we then get is that velocity is equal to the speed of light times delta lambda over lambda. Now, you don't have to convert delta lambda over lambda to meters because it's only a ratio, and the ratio in centimeters would be the same as the ratio in meters. So the speed of light is 3.0 times 10 to the 8th meters per second. We've calculated the wavelength shift to be 0.01, and the original wavelength was 21. So we have to perform this calculation now. So it's equal to 3.0 times 10 to the 8th divided by 21. And now 0.01 is equal to 10 to the minus 2. So I just replace that with 10 to the minus 2. Now we have some powers of 10 to combine. And a to the n times a to the m equals a to the n plus m. So 10 to the 8th times 10 to the minus 2 equals 10 to the 8 minus 2 equals 10 to the 6. To minus the minus 2, 10 to the 8 minus the minus 2, because this is a minus 2 power, so it is equal to a 10 to the 10th. So we now have 3.0 times 10, I messed that up, I'm going to restart. So 10 to the 8th times 10 to the minus 2 is equal to 10 to the 8th minus 2 equals 10 to the 6th. So 3.0 times 10 to the 6th divided by 2.1. Now 3.0 divided by 2.1 is 1.2. And on the bottom, we have something that's not here right now. Okay. So this is 1.2 times 10 to the 6th And this is the speed of the object that we've now calculated, and it is in meters per second. Okay? So we've calculated this speed, 1.2 times 10 to the 6 meters per second using the Doppler shift. Now the last problem I want to do is from chapter 7, and it is on page, chapter 9 actually, on chapter 9, and I misspoke again, it's a chapter 7 problem. Okay. And it is number 7. So it is on page 198, number 7. So, chapter 7, page 198, number 7. So let's read the problem. A laser pulse takes 2.56 seconds to travel from the Earth to the Moon and return. Use this to calculate how far away the Moon is. How might this time delay affect conversations between an astronaut on the Moon and an astronaut back on Earth? So use this time delay of 2.56 seconds. First, we can answer the qualitative questions. If the astronaut is talking to you and you receive the signal 2.56 seconds later, then he's going to be waiting for your response that amount of time, and you're going to be waiting for his response that amount of time. So it means that you will send your message, but you won't get the response back for 2.56 seconds. He will send his answer, but he won't get your answer to his answer back for 2.56 seconds. So these would just be delays that you deal with. We use the same thing all the time when we use satellites for our phone conversations or CNN broadcasts. We're used to these time delays. The question wants to know how far away the Moon is. How far away the Moon is. So once again, we have speed is equal to distance divided by time. And if we multiply both sides by time, then we see that on the right-hand side, they subtract out, and that we have that distance is equal to time times speed. Now the speed in question is the speed of light, 3.8 times 10 to the 8 meters a second. But they want to know how far away the Moon is. So how long did it take the signal to get to the Moon? Well, the 2.56 seconds was a round trip. So to get the one way, you have to divide it by 2, 1.28. So is equal to the distance. So you multiply 3.8 times 1.28, and you use your calculator as before, and you will get 3.84 times 10 to the 8 meters. Is equal to the distance. So that is the answer to this problem as well. So we've done some 4 or 5 example numerical problems.